Okay. All right, so I think we're all set there. So the title is called Implicit Differentiation, which we need to make sure we understand the English behind what we're doing here. So explicit means in plain language or easy to use, kind of obvious, okay? Explicit, that word explicit means it's very obvious and easy to see. So when I'm in mathematics, when I'm talking about y is given explicitly in terms of x, that's the type of equations we've been studying all along. So y, oh, forgive me. So most of the equations we've been studying are explicitly in terms of x. So y is given to you as some sort of combinations or algebraic operations of x, okay? It's very explicit that we can see it. Doesn't matter what that function is, you always see y equals and then an explanation of what y is or how to find y. These are all explicit ones. Even longer equations like polynomials, even things like that are all explicitly in terms of x. Y is given explicitly in terms of x. So the opposite of explicit is implicit. So it's not easy to see, or maybe there's some implied information. So examples of that we would have saw in grade 9 or grade 10. An equation like this. So if you remember back to grade 10, this is actually the equation of a circle. But you can see how the y is not easy to see. You can't see the relationship of y because it is inside this other type of function. So it's not explicit, it's implicit. It's within that function. Even grade 9, when we did standard form, y is not explicit. You can't see y by itself. It is within a different form, and so it's implicit. So what we've been differentiating up until this point have all been explicitly written, functions that are explicitly written. What we're going to learn today is how to differentiate, in this case, when y is not explicit, so it's implicit. That's what we're going to tackle today. Okay, this is again another decision that we have made that kind of is an addition to our curriculum. Our curriculum says if you end up with an equation that is written implicitly, rearrange it and differentiate it explicitly. So we could take this equation and rearrange it if I wanted. So I could go and rearrange this and say it's y squared equals 25 minus x squared, and say y equals plus or minus the square root of 25 minus x squared, and then go off and differentiate. But you can see that differentiating this is going to be a lot different than, or a little bit more challenging than what I'm going to show you how to differentiate. So again, instead of hiding some calculus from you because it's not in the curriculum, I think it's best to understand the calculus so that we can make these questions easier. Okay, so this is one of those sort of topics. We're not going to go down the route. The same with like the quotient rule. Remember, the curriculum says change all quotient rules to products. Well, I think that makes life easier, or like life harder, instead of just learning the quotient rule. Same thing here. We're going to learn to implicitly differentiate because it's going to be easier than doing it this long way. So what we're going to do is differentiate y in terms of x. So remember that notation that you see in this example, dy by dx, is the same as y prime is the same as f prime at x. But it's written just a little bit differently. So we're still differentiating. The difference, of course, is the equation we're starting with is not written y equals or f at x equals. It's written like this, implicitly. So first, we have to recognize we're differentiating y with respect to x. So here's how implicit differentiation works. We pretend that every variable we see is an x, just like we would if we had a regular thing like y equals x squared plus 3x minus 5. Okay, we all see these x's. We know how to differentiate this. You just did a big test on that. Okay, we're going to pretend that every variable we see is an x, and if it's not, we're going to make one small adjustment. So this question says we're differentiating with respect to x, so we pretend that every variable is an x. So in the first part, you see x squared. Well, good news, I know how to differentiate that. That is an x. The derivative of x squared is just 2x. Next, I see a y squared. Now I'm supposed to imagine that it's an x. So if it was an x, it'd be x squared, and the derivative would be 2x. But it's a y, so the derivative is 2y. But because I'm differentiating with respect to x, and the variable isn't an x, I have to add one little addition to this differentiation. I add dy by dx. Because I'm not actually differentiating with respect to y, which is what I would do if it was a y variable, I'm actually differentiating with respect to x, and when the letter is not the same, I have to add this dy by dx after it. Okay? And then equals, now 49. 49 is not a letter, so it doesn't matter. I just differentiate 49 normally. And the derivative of 49 is 0. Right? Remember, all constants graph like this, and all slopes of tangents for this are 0. So it doesn't matter whether I'm differentiating with respect to y or x or anything else. A number is just still a number. I differentiate that, it's 0. Okay? So that's the reasoning behind it. When you actually go off and do it, though, you essentially differentiate just like you normally do. The only catch is if you're differentiating with respect to x and you see a y, you do it normally, but add this little dy by dx. If you saw a z someplace else, you would go dz by dx. Okay? Any letter that's not an x gets this little addition. And now, remember, I'm trying to find this. Well, I found that variable right here. Which means I have to rearrange my equation so that that is by itself. So even though I've taken the derivative, I haven't actually found the dy by dx. I need it by itself. So to do that, of course, I'm going to isolate. So I see a 2x here, so I'm going to subtract both sides by 2x. So take it to the other side. So dy by dx equals negative 2x, because it's plus 2x, so I'm going to take it over there. And this 2y is being multiplied by dy by dx. So, of course, if I want the dy by dx by itself, I'd have to do the inverse operation, which is to divide. So to get rid of this 2y, I have to divide. And what I have then is my answer. My goal was to find dy by dx, and I found it. The only thing left is to do any reducing that could happen, and since I have a 2 on the top and a 2 on the bottom, I can cancel those, divide both the top and the bottom by 2, and get a reduced version of dy by dx as negative x over y. And that is the derivative of this implicit equation. So if I want to write out the steps, you're going to differentiate both sides with respect to x. So WRT means with respect to x. And then step 2, isolate for dy by dx. And when I differentiate with respect to x, if your letter doesn't have an x in it, you have to add your dy by dx. If it does have the x in it, you don't have to add anything else. Technically, we actually did add it. We add dx by dx here, but dx by dx is like a fraction that disappears. So it's unnecessary to say that step, so we don't. But when the letter is different, we have the dy by dx. Okay, so let's try another one. Remember, we're solving for dy by dx. We are differentiating the y equation with respect to x. All right, would someone like to then walk through this with me? Oh, we have a hand up first. Kelsey.
Will it always be with respect to x, or can it be with respect to y?
It can be with respect to y. Later on, you'll see ones we're going to do will be with respect to t. You'll see y later on. It can be with respect to whatever, but most often when the original questions we're going to do are going to be dy by dx, just because it matches what we've been studying before. Good question. Okay, someone want to then differentiate this with me?
I can try, no promises. But
Nope, that's fair. Okay, so 2x squared, what's the derivative of that?
4x?
Right, and I don't need anything added on to that, right?
No.
Right.
Plus 2y. Bracket dy over dx.
Exactly. Good?
Plus 3, and then dy over dx.
Yes.
Equals 0.
Perfect. Thank you, Jacob. Exactly right. Okay, so we just differentiate it like it's a regular polynomial. Wherever there's an x, you differentiate normally. If it's not an x, you have to add that dy by dx. Now the trick in this is isolating for dy by dx because it's in 2 spots. So the first thing I'm going to do is get rid of that negative or that 4x and put it on the other side. So dy by dx plus 3 dy by dx, and I'm taking that 4x and bringing it over here and go negative 4x. Now I need to isolate for dy by dx by getting it by itself, but since it's in 2 terms, I'm going to take it out as a common factor. So you see how this is here and here, so I can take that out as a common factor, dy by dx. Divide it out just like you would have divided out any other common factor. And when it gets divided out of the first term, you're left with just 2y. And when it's divided out of the second term, you're left with just a 3 equals negative 4x. Whenever you take a common factor out, you can always check to see if you did it properly by putting it back in your head. So just rainbow this back. Yes, you see there, you get that. Rainbow that back. Yes, you get it. So I have taken it out properly. By taking it out as a common factor, there's a single dy by dx out by itself, which is being multiplied by this whole term. And so when I bring it over here, I'm going to have to divide. So dy by dx equals negative 4x divided by this whole thing, 2y plus 3. And there is our answer. So again, I can't stress enough about how this is the same differentiating we've been doing, but when you see a different letter, you just got to add that dy by dx onto it, and then the challenge of just isolating for dy by dx. And you'll get something that looks very different than the original, but of course it's different because of what we have to. And imagine how we would have all the work we would need to do to try and rearrange this into y. Like it would be y squared, it's gonna be too hard. Minus 2x squared, and then take out a y, it still doesn't work. Like it's too much work to try and isolate for y, and then I haven't even taken the derivative of whatever I come up with. So it's definitely not a great strategy to try and isolate for y before you differentiate. Let's just use implicit differentiation to get an answer we can manage. Here's another example. And since it's differentiation, it doesn't matter that it's implicit differentiation, it's differentiation. So all the rules we learned last unit, like product rule, quotient rule, chain rule, all of those still apply. We just have this one little added layer. So in this case, again, let's use implicit differentiation. I see a product of two functions. I see an x squared and then just a y. So I'm going to differentiate that using the product rule. So the product rule says derivative of the first, which is 2x, times the second. I'm not differentiating, so I don't need anything else on that. I'm just saying times the second, plus the derivative of the second. Now, the derivative of the second is a y. So the derivative of that is 1, but I need dy by dx. Times the derivative, or times the first, equals, and then the derivative of 12 is just 0. So again, let's see that sort of step. So the derivative of the first is 2x times the second. Not the derivative of the second, just the second. That's why it's just y. I don't have any dy's by dx's or anything like that. I just write it down. Then I differentiate the second. Well, the derivative of y is just 1, but since I'm differentiating with respect to x, I need the dy by dx. Derivative of the second times the first, as is, and we get that. And then, of course, on the other side is just 12, so the derivative of 12 is 0. All right, now we got to clean up and isolate. So I don't know if it's worth writing this, but I'm going to write it down anyways. 2xy plus dy dx times x squared equals 0. I need to isolate the dy by dx, so I'll isolate the term that has dy by dx in it by itself. And then I've got to get this 2xy to the other side, so it becomes minus 2xy. And then it's being multiplied by x squared, so I'm going to have to divide by x squared. So dy by dx equals negative 2xy over x squared. Any questions? Okay, so and then what we do is we just keep doing different questions that use different rules, differentiation rules, with implicit differentiation. So I can go to a fourth example. And now here's an example with the power of a function rule. This is actually a circle. Well, circles are curves, and you can imagine tangents all around circles. So we can come up with all sorts of different tangents around these circles. But let's find the equation that would represent all the different tangents. So again, I'm going to apply all the same rules that I did before. It's just when I'm differentiating with respect to x and I see a y, I have to add that dy by dx. So in the first, something squared. So again, I don't care what letter it is. I know that that is 2 bracket to the power of 1. Then I go inside and write in exactly what I see. I don't care that it's an x or a y yet, because it's exactly what's inside, times the derivative of the inside. Now I care. The derivative of y plus 3 is 1 dy by dx. Because the derivative of y is just 1, but since I'm differentiating with respect to x, I need that dy by dx. All of that is the derivative of this thing. Luckily, I'm adding it to a different one, so I'm not multiplying these, where you would have to do the derivative of the first times the second plus derivative of the second times the first. I'm just adding it. So the second half is like its own little question. And this one is with respect to x. So first, outside, power of a function rule, the 2 comes down, leave the inside alone. Now differentiate inside, the derivative of x minus 4 is just 1. Since I'm differentiating with respect to x, I don't need any additions to that one. That's just fine. Equals, and the other side is 8, and the derivative of 8 is just 0. So a little bit more work to isolate for dy by dx, but nothing we can't handle. I'll clean it up a little bit first by seeing a 2 times a 1. So that is 2 bracket y plus 3 dy by dx. Again, a 2 times a 1 is 2. X minus 4 equals 0. Remember, if we can do simple rainbow, we do simple rainbow. This is simple rainbow. So I'm going to do a little simple rainbow. Again, just tidying things up before isolating. So simple rainbow is 2y plus 6. Again, remember my answer for a rainbow should be in brackets. Plus, and then over here, a 2x minus 8 as a simple rainbow. I'll put it in brackets if I need to. Equals 0. So I tidied it up just to make my isolating a little bit easier. So the 2y plus 6 dy by dx is by itself. In order to keep it by itself, I need to move this to the other side. So I'm going to minus a 2x and add an 8. Okay, I'm subtracting both of these things from both sides. So I'm subtracting the negative, and I have to add the 8 to move it. Now I have something being multiplied by dy by dx, so I divide. And there is the dy by dx, the derivative of this one. So really, all these examples are just showing you that the same differentiation rules we learned last unit apply in implicit differentiation when your variables are slightly different.
Shouldn't you simplify that?
Yeah, actually, that's probably a good point. Divide everything by 2, is that what you think?
Yeah.
Yeah. Yeah, good.
Or
Yeah.
possibly negative 2 to make the x positive, or unless you don't need that, I don't know.
Right, and in fact, that would be fine. These aren't quite as picky as some of the other stuff, because then we'd have to make the bottom negative 2, right? So I think we'll leave it as this.
Okay.
Good question. Okay, and then the last example I'll do with this brings back one of the questions that I promised we would see every single unit, and that is find the equation of the tangent. So you had a couple of these on the test, find the equations of the tangent line to the curve. The only difference between this one and the equations that you would have done on the test is the equation is not explicitly in terms of y. It's implicit, but our strategy is exactly the same. I'll give you a second to copy that down. So find the equation of the tangent line to the curve, x squared plus 4y squared equals 25 at the point -3, 2. So our goal in all the other questions was to come up with the slope first. And so in order to get the slope, we of course need the derivative, which is the equation for all the slopes. So we'll first find the derivative and then find the specific slope at that point that's there. And finding the derivative here is finding dy by dx. So I first am going to go off and differentiate. Let's see if someone would like to differentiate this implicitly with me. Josie, how about you? Oh, Jacob, you've already done one, thanks. Josie said she wanted to do it too.
Would it be 2x plus 8y bracket dy by dx equals 0?
Perfect, thank you. So then we, of course, will isolate for dy, so we'll leave the 8y dy by dx there. Take the 2x and bring it to the other side, so minus 2x. And then I want dy by dx by itself, so I have to divide. So that's the derivative, which is the equation or the dy by dx that describes all of the different slopes. But I want specifically the one that goes right there. And this time, normally I would just need to sub in an x because our equation was explicit. But now we're subbing in a y. Question, Kelsey?
Can't you simplify that?
Yes. And you guys are doing a better job of catching these simplifying. Thank you. Good. So that'll make our life a little bit easier. But now we're going to sub in the point. Normally we would just sub in an x, but here my equation has x and y, so I'm going to need both of them to sub in. So sub -3, 2. So now I switch from finding the equation to finding the slope. And the x is -3, so it's negative x. So, or sorry, negative 3. All right, we're plugging in -3. And y is 2. And so this becomes 3/8. So the slope of the specific tangent at the point -3, 2 is 3/8. That puts me halfway to being done. Y equals 3/8 x plus b. Now I'm going to use that same point and plug it into my equation of this line to figure out the y-intercept. So the 2 is, or the y is 2, 3 over 8. The x is -3 plus b. A little annoying that I have a fraction, but nothing I can't handle. Multiplying by 3 means I multiply the top, so that's -9 over 8 plus b. I'm going to have to bring that -9 to the other side, so it's 2 plus 9 over 8 equals b. To add them, I need a common denominator, so 16 over 8 plus 9 over 8 equals b. That's going to get me 25 over 8 equals b. And take my new slope. Oops, 3 over 8. X plus 25 over 8. I'm okay with this question being left in y equals mx plus b. Your textbook would rather it be in standard form. To put it in standard form, we can't have any fractions. So they would multiply everything by 8 and get 8y equals 3x plus 25, and then would rearrange it to 3x minus 8y plus 25 as the answer that would be in the back of the book. Okay? That's only in case you wanted to check your answers. I'm okay with you leaving it in y equals mx plus b. All right, let's just check this out on Desmos. Desmos will just tell us the slope. It won't tell us the equation, but we're hoping to get 3 over 8 for our slope. So let's go and check it out. What was our question? X squared plus 4y equals 25. So, oh, this isn't going to work. Yeah, so in order to make this work, I got to rearrange because Desmos doesn't do it implicitly either. So I'm going to have to actually rearrange this. Equals squared. All right, so what you're seeing is just the top half of the ellipse. This is actually an ellipse. not a circle. If I want the bottom half, I would make a second one with a negative. But the point being is you can see the slope of the tangent right there at -3. You can see that the slope is 3 or 0.375, which is the same as 3/8. So it does confirm what we want. But you can see how doing this implicitly, which is what I need to get my tangent, do this implicitly makes our math a lot easier, or more difficult, excuse me. Explicit is more difficult. Implicit is a little bit more manageable. Okay? All right. So, again, period 4 will be a chance for you to practice. We're not going to do these ones. We're going to, and you don't need to worry about this one. Number 2, A, C, E, I, and K. Number 3, A, B, and 8. Okay, so this implicit differentiation is a new way to differentiate. We had to just get a little bit of practice with that now so that we can apply it this afternoon. So we'll be doing some more application questions this afternoon where this type of differentiating will come into play. Okay, so hopefully this was not too bad to do after our test, and we'll give you the 45 minutes for lunch now, and we'll meet back at 11:45 where we'll do our application lesson this afternoon. If anyone has any questions, they can stay on. Otherwise, I'll see you after lunch, 11:45.